here's the Faraday's Law lab. To begin, our mission is to observe a magnetic braking of a magnet falling through an aluminum tube, and then code up a model that sort of represents how long it takes to fall through the actual tube, and as well as observe how long it takes in real life to fall down the tube. Our models and principles here include Faraday's Law, magnetic flux, the dipole model for magnets, as well as Lenz's law. What will happen here is essentially we will observe that a bar magnet falling through a conductive tube does in fact slow down due to magnetic braking, plus our model is very accurate to observe how long it takes to actually fall down the entire tube and predict that accurately. Our ideas here include the idea of Faraday's law, which says that a time-changing B field produces another curly electric field that causes another B field to happen in turn that affects the motion of the thing that falls down and causes a different motion in that falling object. Flux is defined as the how much stuff passes through a given area, and magnetic flux is defined as the integral of B dot dA, also called phi of B. All magnets are dipoles, positive and negative ends within them because natural life does not have monopoles. They don't exist in real life at all. So see here, the dipole looks like this with north and south end poles and E fields and B fields around it. And Lenz's law states that nature abhors changes in flux, so it tries to prevent that from happening at all by doing counteractive movements that reduce the amount of flux change in general. For experiment details here, the system is the bar magnet itself. Everything else in surroundings, including the foil and everything else that surrounds or causes a force on the actual magnet. My procedure was taking a bar magnet and dropping it through the aluminum foil 5 times, making sure to record the amount of time it takes to fall down the entire thing, and record the average total as well, which was in fact 0.302 seconds, which is longer than it takes to just drop it down in plain air, for example. So it is in fact a visible, tangible force on the bar magnet's motion based on the magnetic flux of the induced current within the aluminum coil. My code looks like this, for example, and it shows here in GlowScript it yields a fall time of 0.257 seconds, as well as code is right here for how I made the actual geometry, as well as parameters for numbers, as well as mass and mu magnetism, etc. And here's the actual code to represent how I made the functions to calculate dipole B field, as well as how to calculate the derivative of flux at a given time based on where we are currently at in the coil, as well as how strong the current B field is at that point within that loop. So here's the actual result from the code implementation. We see that the falling of the dipole bar magnet falls in this tube right here and shows that the red part here is the positive end of the falling bar magnet. And the velocity graph versus time shows how it's linear over time and shows that there's a decrease in velocity, becomes more negative over time because it falls down faster as gravity and magnetic field become a giant force that causes this sort of movement over time. And the code here represents how I made the various codes for gravity force as well as forces caused by magnetism and currents and loops, and the overall force can be used to determine how fast it falls down using velocity and position update formulas based on Newton's laws of motion. Errors here might include, first of all, I had a 17.5% error. That was because of many human errors in my experiment, as well as based on, in general, just man-made errors. And it was a pretty accurate model because of this very generally pretty small error I had from my calculation, as well as because it's, pretty accurate in predicting the overall trend of how fast it falls. However, errors might arise because of things such as I did not measure the actual mass of the magnet in my code, but rather estimated it using density as well as volume in my formula, and also dropped the magnet slightly above the tube's opening because that sort of made the time longer than it should have been, as well as I stopped it after it fell out of the thing, so it became a lot more of a skewed time distribution. And the provided foil was actually less than 1 centimeter in thickness, which could have been affecting how fast it took for it to fall down the entire tube. Therefore, it's deviates from the ideal conditions of the tube structure in an ideal conducting tube. That's why it's a little bit off in that dimension as well. And what if the resistivity of the conductor was in fact changed to 0 instead, or almost 0? As Ohm's law states that V equals I times R, making the resistivity 0 would cause the current to become very high and become a much more high EMF as well that is produced from the current, which causes more braking and as well as a slower overall fall time for the actual magnet. And what if holes or slips are cut into the actual tube as well? Well, that would cause certain loops to have no such thing as B field at all because they have no complete loop at that point, which would cause even less B field opposing it and therefore cause a faster falling down time of the magnet and less time to fall down to the bottom of it due to the less P field at that point because there's no current at all at that cut or slip points. In conclusion, we have braking systems that cause very cool things in the real world that cause braking in things like vehicles as well as machinery, And they're very helpful to help actual things in real life work, all thanks to Faraday. No matter which orientation the bar magnet is placed in, it will experience the same B field and braking because as it falls down, it has the same orientation and will eventually realign itself to fall in the ideal direction. And also we have velocity, but time gravity is very linear because of constant force due to combined gravity as well as magnetism. And that's about it for this. Thank you for watching very much my video, and goodbye. There we go.